Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about valid power spectral densities or not. And this is the previous examination question. The example is, first bit is Sxx of omega is equal to omega square by omega power 6 plus 3 omega square plus 3. And second bit is Sxx of omega is e power minus of omega minus 1 whole square. Third bit is Sxx of omega is equal to omega square by omega power 4 plus 1 minus del of omega. And fourth bit is Sxx of omega is equal to omega power 4 by 1 plus omega square plus j plus omega power 6. So coming to the solution, first bit solution. So given that the power spectral density is Sxx of omega is equal to omega square by omega power 6 plus 3 omega square plus 3. So find out the given function is valid power spectral density or not. So using properties of the power spectral density, the power spectral density is an even function of omega. That is Sxx of minus omega is equal to Sxx of omega. If that condition is satisfied, hence the given function is a valid power spectral density. Otherwise, not a valid power spectral density. So first we can calculate Sxx of minus omega value. In the given Sxx of omega, omega is replaced by minus omega, we get Sxx of minus omega. So Sxx of minus omega is equal minus omega square by minus omega power 6 plus 3 into minus omega square plus 3. So minus omega square is omega square, minus omega power 6 is omega power 6, minus omega square is omega square plus 3. So this RHS term is the given power spectral density, that is Sxx of omega. So now here Sxx of minus omega is equal to Sxx of omega. The condition is satisfied. So the power spectral density is an even function of omega. Therefore, the given power spectral density is a valid power spectral density. And second bit solution, given that the power spectral density Sxx of omega is equal e power minus of omega minus 1 whole square. In the same process, first calculate Sxx of minus omega. In the given power spectral density, omega is replaced by minus omega. We get Sxx of minus omega is equal e power omega is replaced by minus omega, e power minus of minus omega minus 1 whole square. So now they take the common minus, e power minus of omega plus 1 whole square. So this RHS term is not equal to given power spectral density. So that is not equal to Sxx of omega. So now here the condition is not satisfied. The power spectral density is not an even function of omega. So therefore the given power spectral density is not a valid power spectral density. And third bit solution, given that the power spectral density is omega square by omega power 4 plus 1 minus del of omega, and substitute omega is equal to 0, Sxx of 0 is equal to 0 square. 0 square is 0, 0 by something 0 minus del of 0. Del of 0 value is 1, so which is equal to minus 1. So using one of the properties of the power spectral density, the power spectral density is always non-negative, that is greater than or equal to 0. So now here at omega is equal to 0, the power spectral density value is minus 1. So the given power spectral density is not a valid power spectral density. And fourth bit solution, given that the power spectral density is omega power 4 by 1 plus omega square plus j plus omega power 6. So using one of the property of the power spectral density, the power spectral density is a real valued function. The power spectral density is a real valued function. So now here from the given data, the power spectral density is not a power spectrum because it is not a real valued. So it means in the denominator term, j imaginary part is there. So because of that, the given power spectral density is not a power spectrum. So because of that, the given power spectral density is not a valid power spectral density.